Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. In this video, I would like to discuss about numerical solution of first order ODE. So the topic that we will cover in this chapter, we will start with the introduction first, and then Euler method, and the last one is a Ranch-Kata method, or we call it as RK4. Here are the objectives of this topic. The first one, everybody must know how to find the solution of single ODE by using Euler method. Then, everybody also must know how to find the solution of a system of ODEs by using Euler method. Objective number 3. Everybody must know how to find the solution of single ODE by using fourth order Ranch-Kata method. And lastly, everybody must know how to find the solution of a system of ODEs by using fourth order Ranch-Kata method. Okay, for the introduction first, ODEs refer as a rate of equation. It expresses the rate of change of a variable as a function of variables and parameters. ODEs provide a tool for better understanding the behavior of many biological and physical systems around us. It forms the basis of simulation experiments in a realm where the experiments are often impractical or unethical. By solving the ODEs, one can identify trends and make forecasts about the future path of the process. Given here, dy dx is equal to fxy, where the initial condition yx naught equal to y naught is our general form for ODE. Here the applications of numerical solution for first order ODE. The first one, flow due to a falling heat. So this is the first order differential equation where widely used to compute the depth as well as the time required to drain the tank. Second one, we can calculate falling paracutis where the relation is the acceleration of the falling object to the forces acting on it. And the third one, we have Lotka-Volterra equation. So from here, we have two first order differential equation. So this is the example of system of two first order ODE, where it describes the dynamics ecological system prey-predator interactions. So in this topic, we will cover two methods. The first one is an Euler method, and the second one is a fourth order Ranch-Kata method, where we will cover for single equation and also system of equation. Okay, for Euler method. Euler method is one-step method that can be formulated in general as yi plus 1 is equal to yi plus phi h, where h is a step size and phi is a slope estimate. A new value of y plus 1 is extrapolated from n all value of yi over a distant h. For Euler's method, the first derivative dy dx is equal to fxy yi provide a slope estimate at xi such that phi is equal to fxi yi. Okay, Euler method is the most simple iterative method for approximating the solution of an initial value problem. So here is the formula for Euler method, where fxiyi is the differential equation evaluated at xi and yi. If we see this figure 1 graphical illustration of Euler's method, the new value for yi plus 1 is predicted using the slope fxi yi to extrapolate linearly over the step size. Okay, for better understanding, let's try to solve one example. Approximate the solution of the following ODE. So this is our differential equation. dy dx is equal to exponent minus x minus y, where the initial condition given to us when x is equal to 0, y is equal to 2. For the interval, x start from 0 until 2 by using Euler method. Given also our step size, h is equal to 0.5. So for the first step, let's sketch our number line. Okay, so I start with x naught is equal to 0. The increment is 0.5. So x1 is equal to 0.5. x2 is equal to 1. x3 is equal to 1.5 and x2 is equal to 2. When x not equal to 0, so we have our y naught. So y naught is equal to 2. So we are going to find the value for y1, y2, y3, and also y4. So what is the formula for Euler method? So for Euler method, the formula is yi plus 1 is equal to yi plus f xi yi multiply with h, where xi plus 1 is equal to I plus. So let's start the calculation. Start with when I equal to 0. When I equal to 0, so we will have x0 plus 1 is equal to x0 plus h. So we will get x1 is equal to x0 plus h. So substitute the value. So x1 is equal to x0 is equal to 0. H is equal to 0.5. So x1 is equal to 0.5. So we have x1 equal to 0.5. So now we are going to find our y1. So by using this formula, when I equal to 0, so I will have y1 is equal to y0 plus f x0 y0 multiply with h. Let's substitute the value that we have. y0 is equal to 2. F x0 is equal to 0. y0 equal to 2. And h is equal to 0.5. So now we are going to substitute the value x equal to 0 and y equal to 2 into our f. So what is our f? Function f is our dy dx. That means dy dx is equal to fxy. That means fxy is equal to exponent minus x minus 2y. We just substitute the value x and y and then use your calculator to calculate everything. So your y1 is equal to 0.5. Now continue the calculation. So we already get the value when x1 is equal to 0.5. The value for y1 is equal to 0.5. Now when I is equal to 1. So x2 is equal to x1 plus h. So x1 0.5, h is 0.5. So x2 is equal to 1. So y2 is equal to y1 plus f x1 y1 multiply with h. y1 we already get previously 0.5 plus f x1 is equal to 0.5, y1 is equal to 0.5 and h is equal to 0.5. So just substitute 0.5, x 0.5 and y 0.5 into our f, and we got the value for y2 is equal to 0.3033. Okay, so you just need to continue the calculation with the same formula. Okay, when I equal to 2, okay, so you will get x3 is equal to 1.5, y3 is equal to 0.1839, and lastly, when I equal to 3, you will get x4 is equal to 2 and y4 is equal to 0.1116. Now, let's try to solve one application problem. Solving the initial value problem of following parameters by using Euler method. So this is our differential equation. dv dt is equal to g minus cv over m. This one also will be our function f dv. Given that c is equal to 3 kg per second, g is equal to 9.8 meters second minus 2, and our mass is equal to 75 kilogram. For time start from 0 until 10, and we need to use a time step of 5 seconds with a 0 initial velocity. So for the application problem, for the first step, let's list all the information that we have. Okay, so this is our function dv dt is equal to g minus cv over m. Let's substitute all the information we have. So dv dt is equal to 9.8 minus 3 over 75v. Okay, and we have the interval start t from 0 until 10. Our step size is equal to 5. And what is the initial condition? So initial condition is when t is equal to 0, v is equal to 0. Okay, so now let's sketch our timeline. Okay, so our timeline. So we start with t naught is equal to 0. And the step size h is equal to 5. That means t1 is equal to 5 and t2 is equal to 10. So when t equal to 0, our v is equal to 0. So we are going to find the value for v1 and v2. So when I equal to 0, so ti plus 1 is equal to ti plus h. That means t1 is equal to t naught plus h. So we have t naught is equal to 0. H is equal to 5. So t1 is equal to 5. Here. Okay, we are going to find when t1 is equal to I. So what is our v naught? v1. Okay, when I equal to 0, so v1 is equal to v naught plus f t naught v naught multiplied with h. So value for v naught, okay, is equal to 0 plus f. T naught 0, v naught also 0 multiply with what is our h? H is equal to 5. Okay, so we just need to substitute 0 and 0 into our function, our differential equation here. So our v1 is equal to 49. Okay, so then we just continue. When I equal to 1, so we can calculate our T2. So T2 is equal to 10. So what is the value when T equal to 10? So V is equal to, V2 is equal to 88.5.